Let's talk about power series some more. So first of all, the word analytic is what describes the kind of function for which we can construct a power series. So analytic means that the function has continuous derivatives of all orders. So the familiar functions in the trig class are analytic. For example, sine, derivative is cosine, and you keep going back and forth. It's either sine or cosine with a plus or a minus. And you can do that the rest of your life if you can't think of any better way to spend it, saying sine and cosine. So the others also, the derivatives are more clumsy, but you can do, at least with product rule and quotient rule to help you, any order derivative you want, at least inside of intervals. With the other four trig functions, you have your vertical asymptotes. So when you say it has derivatives, it's in the domain of the original function, so not at the asymptotes. For e to the x, the derivative is e to the x, however you want to say it, how many times. And for the logarithm, you get 1 over x, and then you can do the derivative of x to the minus 1 power, and then the derivative of that, and on and on and on, as long as x is positive. And so the idea of an analytic function is something that is actually what we've had all along without saying the word. So if you have an analytic function, then you can construct either of two kinds of power series, one called the Maclaurin series, the other called the Taylor series. The Maclaurin series mathematically is a special case of the Taylor series, but the people introduced the series separately, and so the names still apply. So say a Maclaurin series then for analytic f of x is a power series in powers of x, whereas a Taylor series is a power series in powers of x minus a. And you see, if a is 0, you're back over here. But this allows for something other than just powers of x. It could be powers of x minus 1 or x plus 2 or something like that. So the Maclaurin series then that corresponds to f of x looks like this. Coefficients C0, C1, and so on, which we still have to determine, and then the powers of x. Well, the way that you can determine these coefficients is use the derivatives, the fact that the thing is analytic, so you can get the derivatives. And this was really very clever to think of this the first time. You see, what you might think you were going to do is solve simultaneous equations. So for example, assuming you had a value for f of 1, you could say, well, f of 1 would be c0 plus c1 plus c2 and so on. And then if you had a value for f of 2, you could write another equation and so on. The problem is that you have literally infinitely many terms here, and so trying to do it with simultaneous equations, you'd be talking about infinitely many equations and infinitely many unknowns, and that doesn't sound too promising. But this, what you can do is really very clever, because remember that analytic means that there are all these derivatives, and it also means that the function's continuous. So it means that there is a value f of 0 that you would know, and if you put 0 on the right, all those terms are gone. So the first term here is whatever is f of 0. So you could get that. For example, if you're doing the Maclaurin series for the sine, this would be 0 because sine of 0 is 0. Then go ahead, differentiate whether you substitute the number here that you've just found as f of 0 or not. Doesn't matter, because if you differentiate, that is derivative of a constant, which is gone. Then this gives you c1. Then this gives you 2 times c2 times x. This gives you 3 times c3 times x squared, and so on. And so f prime of 0, put 0 there. This will be a number you know, and that'll equal c1 because you'll have 0, 0, 0, and so on. So your first constant is your function of 0. Your second constant is your derivative at 0. And then keep going. Go back to this line and do the derivative. So you get f double prime. Whatever this is, the derivative is 0. Then here, the first time, you got 2c2x, so the derivative of that is 2 times c2. And if you went a little further, you see this one would have given you 3c3x squared, then the derivative here brings the 2 down. You'd have 2 times 3 times c3x. And then in the same way, here you'd have 3 times 4, c4, and then x squared. So now you'd have 3 times 4, c4 x squared for your f double prime line. So put 0 there, and so on across, and you see that what you have is c2 is second derivative over 2. Go again. So differentiate here, the derivative of that number is gone. This will give you 2 times 3 times c3. This will give you 2, 3, 4, c4, x, and so on. So put in zeros from this point to the right and solve for c3, and that would be the third derivative over 2 times 3. And it isn't wrong if you say 1 times 2 times 3 instead of just 2 times 3. If you put the 1 in there, then you can write factorial. So your pattern is that the nth coefficient is the nth order derivative calculated at 0 divided by n factorial. And you see, if you've assumed the function's analytic, that guarantees you that you have all these derivatives available to use in this formula. You have to do the derivative and then put the 0 in to get from variable to number, of course. To follow this pattern clear through, you define your 0 order derivative, written this way as 1, and also 0 factorial is defined to be 1, so that you can use this symbolism for all the terms that you'll have. So you can write your series then, starting k equals 0, the kth order derivative, where again the 0 order would just be 1, x to the k over k factorial, and 0 factorial would be 1. So In the same way, we can write a Taylor series. The book uses the language of the series of the function about x equal a. What they mean is that when you write the series, you'll have powers of x minus a. So if what you're looking for is a series like this, so again, the first term is what you get if you put a there and there and there and so on. So the C0 is your function at a. Here, remember, your C0 was your function at 0, your f of 0. And there's a mistake there. The order derivative is f of 0, which isn't necessarily 1, like that. When you see what we will have here with the C0 will be f of a, and my 0th order derivative when I get to the general formula here would be f of a. Okay, so then differentiate, same game as with the Maclaurin series. So you'd have f prime, and then you'd have C1, and then you'd have 2 times C2 times x minus a, 3 times C3 times x minus a squared, and so on like that. And if you put a there, and there, and there, and so on, those are gone. So C1 will be f prime at a. So it's the same game, except it's evaluating the function and then the derivatives at a instead of at 0. And again, for C2, take the derivative of this line, and so you'll have f double prime. You'll have the derivative of C1, whatever it was, is gone. Then the derivative here will just give you the 2C2. The derivative here will give you 2 times 3C3, x minus a. The derivative here will give you 3, 4, C4, x minus a squared, and so on. And you put an a there, and so on. And your C2, when you solve for it, will be f double prime at a over 2. And then if you wanted C3, take this line and differentiate again and put in a from here on to the right to get zeros. And so your third derivative, that's supposed to be a and not 0. Will give you 2 times 3 times C3. Once again, it's not wrong if you stick a 1 there, and if you stick a 1 there, and a 1 there, and so on. And if you do, then you can say that your pattern for the nth coefficient is the nth order derivative at a over n factorial. And again, your 0th order derivative would be f of a. And so your Taylor series then, in powers of x minus a, or about x equal a, if you want to say it as the book does, your formula looks like this. And so these are power series. And as a power series, you can find a basic open interval, the same as we were doing last week with power series. The difference is simply that last week we were not talking about how a power series might have been produced as far as corresponding to any particular function. The homework problems that we went through on Friday in, I guess it's section 10.7, were, well, here's a power series, what's the interval of convergence, and then do you have conditional convergence or not at the endpoints, if you remember. You would use either the ratio test or the nth root test, and that would give you a basic open interval, which inside of which you have absolute convergence, because you put absolute value signs on the factors that involve the x's. And then you might have an alternating series at the endpoints, and you might have convergence then at the endpoints as an alternating series, which we called conditional convergence. So we get the basic open interval and check the endpoints. If you call that interval capital letter I, then inside of I, we can work with power series essentially the same as with polynomials, and that's what's over there under the clock, all the things that you can do. So, for example, if you begin with the series for f of x, and so that you could produce the power series, or begin with f of x and then produce the power series, then if you integrate this power series term by term, the series that you form with the integrals corresponds to the integral of the function that you started with. So if you started with the cosine series and integrated term by term, you'll get the series that corresponds to the sine, and so on like that. And you can go the other way. You could start with the sine series and differentiate term by term and get the series for the cosine. Actually, the interval of convergence for sine and cosine is all x, so that for those two, it's true anywhere. You can also do what's called the Cauchy product. You remember clear back in the chapter, I think it's chapter 8, where the tricks for doing integrals, you remember partial fractions, vaguely and unhappily maybe. And you remember with the partial fractions, one of the methods I was showing you was called poles and residues. Okay, that's the same Cauchy. At that time I gave you a Wikipedia handout that had a picture of Cauchy and said a little bit about it. So he was a French mathematician who lived now, well, I suppose he would have been born about 200 years ago, right now. So anyway, for example, your Maclaurin series, see, it's powers of x, so it's a Maclaurin series, for sine x goes like this, and for cosine x, it would go like this. So if you wanted a series for sine times cosine, you could call this thing f of x and say it's an analytic function and start doing the derivatives and produce a series based on this formula. However, you can also get that same result by simply taking a few terms of each of these as if they were polynomials and multiplying them together as you would polynomials. Of course, if you're going to do that, you can only do a limited number of terms because each of these is actually like an infinite polynomial and you aren't going to live that long. And hopefully you can find something better to do with the rest of your life anyway. But you can get as many terms of the first terms of the power series for this function as you would need. You can also do long division. So you could get the first terms for the tangent, which would be sine over cosine, if you started out as if this were a polynomial and you were going to divide it into this polynomial as in long division. And that would get you the same thing as if you said f of x is tangent and then did the power series by doing the derivatives. If you wanted the series for x sine x or some polynomial like that, you could simply multiply x by these terms. So there is only one Maclaurin series or one Taylor series, no matter how you get it, for a given analytic function. In other words, you don't, if you wanted to get the pattern for the Maclaurin series for f of x equals sine times cosine, you have your choice. You can say f equals sine times cosine and do the derivatives and construct your series by taking the derivatives and summing. Or you could take the first few terms of the sine series and for the cosine series, which you can find in your book. If you look in chapter 10 in your book, they have a page where they show you how what the formulas are for Maclaurin series in common use, such as they'd show you this and show you this and so on. So if you took the first three terms, say, of each, and as if they were polynomials and did multiplication, this polynomial by this one, you'll get the first terms of the series the same as if you had called this a function and obtained the terms by differentiation. Or if you were thinking of the terms for tangent, which is sine over cosine, divide, say, these three terms like it was a polynomial into these, and you'll establish the pattern for the tangent series, the same as if you got it by doing derivatives. And quite often we get the power series for a function by manipulating in this way rather than by actual calculations of the derivatives and the actual application of the Maclaurin series or Taylor series formula. So the book, this is section 10.8, I think is where I am. The book has these theorems stated formally of what it is you can do. So theorem 19 in the book is this Cauchy product. The book, I don't think, says the word Cauchy product, but they probably should. So as they write it, you define a function a of x as a Maclaurin series. They, in the way that they've stated their theorems, they're stating them for Maclaurin series, but they're true for Taylor series in general. So a of x is the sum a n x the n. B of x is sum b n x n. So this converges in some interval I1, and this converges in some interval I2. This interval wouldn't necessarily have to be exactly the same as that one. If you were talking sine and cosine, both of these intervals are all x, but for other things, the interval isn't necessarily all x. For example, if you're talking about a logarithm, your x certainly has to be positive, so on, like that. So then inside the intersection of these two intervals, call that an interval I. Then you can say the series Cn(xn) converges absolutely to the product of these two functions, where you would form the coefficient Cn by taking n terms of this and of this as if they were polynomials, and write one of them above the other, and then start doing your products. That kind of multiplication is called vertical format. Let me get some colors and I'll show you how it works. Fortunate, really, from the point of view of trying to teach calculus anyway, that the people in mathematics education have, at least in this country, have decided that the way to teach people how to multiply, say, a plus b times c plus d is to use the rule that we call FOIL, as you know, first, outside, inside, last. Because then you never learn how do you multiply something if there's more than two terms here and more than two terms here. And yet, even if you were trying to do something like the factors of x cubed minus 1, remember you have x minus 1 and you'd have x square plus x plus 1. And how do you FOIL that? Well, you never learn, you see. So what you do is called vertical format. However many terms it is, you put your one polynomial on top and your other one on the bottom, and you start at the bottom left, and you do like this. So then you'll have a row of products that'll be that color. And then you move over one, and you do like this. And you put all the blue ones on the next line, and so on. And you arrange things in columns, if it's a thing of this sort, where you have powers of x, so that you have like powers in the same column. And you just keep on going until you've run across, clear across, left to right, all of the terms in the factor that's on the bottom. So if you had a thing like this, so, for instance, let me go over here where I have a little room and show you fairly simple example from algebra. So take the factors of, say, of x cubed minus 1. So you have x squared plus x plus 1, and you have x minus 1. So what I was saying is, so you do this. So you have x cubed. And then you'd have see, I'm putting like powers in the same column. And I guess the factors that I really want, I guess that's minus. It's going to have to be. Oh no, that isn't what's wrong. This is what's wrong. Just a second, sorry. That's right. And that's right. It's this one that has the minus. Moves the other way. I couldn't see why that wasn't going to work. And so what you end up with then, you add in columns. And this is plus and minus, so that's gone. Plus and minus, that's gone. Minus 1. Well, I wrote the factor down wrong, but you see how the vertical format works. So that's what you have to do with these Cauchy product type multiplications. So theorem 20 then, your series converges absolutely for x less than or equal to some r, then that means that if you replace the x's by some f of x, this is how you would make the power series for a composite function. And if the f of x is a continuous function for all x's in this interval that you have established for the power series, then the power series where you've replaced the x's with this function corresponds to a composite function g of f of x, which you can write this way or this way. So this lets you take a power series and that represents some function and then substitute the x's with, substitute for the x's with some other function, g, and then you end up with the composition, the composite function, g of f. So if your g, for example, were sine, then you could take the terms of the sine series, the Maclaurin series, which again are like these. And so if you wanted sine of square root of x, for instance, you could replace each of these with square root x, and you'd have the power series for the sine of square root x. Or you could replace each of these with log x, and you'd have the Maclaurin series for sine of log x, and so on, like that. Then we have theorem 21 for term-by-term differentiation. So, for example, this is a Taylor series if its powers of x minus a, and you have some basic open interval, which would be if r is the radius of convergence, it's from r minus a to r plus a. And so this is the series for f of x inside of that interval. So then if you have that, you could do term-by-term differentiation, and that produces what you call the derived series, the series that corresponds to the derivative. And that will correspond then to f prime inside of this interval. So if your original series is f of x equals, or f of x corresponds, say, to cn x minus a to the n, then the derived series, the series for f prime, you take the derivative term by term. So you'd have n c sub n x minus a to the n minus 1. So if this corresponds to sine, then this one would correspond to cosine, and then this one would correspond to minus the sine, and so on. And it would be true inside the interval where these series converge, which would be all x if it's sine and cosine, but not necessarily that much of an interval for other functions. You are guaranteed convergence for your derived series interior to the original interval of convergence. So the r minus a to r plus a with parentheses. You might or might not have convergence at the end point. You would have to take your series you got with the derivative and then check the endpoint on that to see if it's convergent at the endpoint. Then finally, the last one says you can integrate term by term, and again, you have some interval of convergence for f of x, so then the integral of f would be what would correspond to the series that you get if you integrate term by term, so add 1 and divide by the new exponent. And that's at least true inside of the interval of convergence of the original f of x. And again, you would have to check at the endpoints to look for conditional convergence. So here's some examples of how this stuff is going to work. Say you started with this alternating power series. It is a power series because it's powers of x and the powers are positive whole numbers, and it is also alternating, as you see. So you could wonder what function it is that this is the power series of. And so the first thing to consider is the interval of convergence. So that would be back to last week. Either you take the nth root test on this, or you do the ratio test, which is what I've done here. And we'll go on in a second. If you do your ratio of the n plus first term to the nth term, you see if your general term is exponent 2n plus 1, and you replace n with n plus 1, put n plus 1 there, then you get 2n plus 2 plus this one, so 2n plus 3. So your next term is x 2n plus 3 over 2n plus 3. The denominator matches the exponent. And then your nth term is what you were given, 2n plus 1 over 2n plus x to the 2n plus 1 over 2n plus 1. And you notice that you're testing for absolute convergence, so you don't worry about sign alternating. And when you divide this fraction by that one and simplify, you'll have the 2n plus 1 over 2n plus 3, and then you'll have x square. The 2n's subtract out when you subtract exponents, and you'll have 3 minus 1. And so this limit that goes to 1, and so you have x squared less than 1 for your basic open interval, and so absolute value x less than 1. So it's minus 1 to 1. You have conditional convergence at the endpoints, because if x is 1, this goes 1 minus a third plus a fifth minus a seventh. That's alternating and decreasing. And if you put minus 1 in, this is minus, and then that's minus with a minus in front of it, so then it's going minus plus minus plus. So that's alternating. So your final interval is actually closed. Okay? So now, differentiate term by term. So the series for f prime, whatever this function is going to go 1, bring the 3 down and cancel, minus x squared, bring the 5 down and cancel, plus x fourth, and so on. Now this thing is a geometric series where the first term is 1 and the common ratio is minus x squared. 1 times minus x squared gives you that. This times minus x squared gives you that. This times minus x squared gives you that. So you got a geometric series there. So f prime is the sum of this geometric series, and your formula from the first section in chapter 10, or no, second section, the formula for the sum of a geometric series when R is the common ratio is any common factor times 1 over 1 plus, or 1 minus, pardon me, your common ratio. So your common ratio is minus x squared, as I say here. So 1 over 1 minus the common ratio, so 1 over 1 plus x squared. So 1 over 1 plus x squared will give you this series. You could get it if you wanted to simply by long division. If you, instead of doing it this way, if you did this, like you would if you were in an algebra class, what goes here, say this is a 1 here, what goes here times that goes under there, and it has to match, right? So you'd have 1 plus x squared. And then you subtract, so you change sign. So what goes here times that matches that. And this times that. And then you subtract. And you see, you just keep going like that, and that'll produce the same thing that I have here. So either way you do it, then the f prime is this geometric series which has sum 1 over 1 plus x squared. So the original function that corresponded to this series is the integral of its derivative. So it's the integral term by term here of the function 1 over 1 plus x squared, which gives you arctangent. So this is actually the series up here then for the integral of this, which is arctangent of x squared plus constant. At x equals 0, arctangent of 0 is 0, and you'd have zeros in all of these places because they're all powers of x, so your constant of integration is 0. So your arctangent series then is like this. And there's a formula then, arctangent of 1 is pi over 4. So Lord Bruckner's formula, as it is called in some books, is pi over 4 is arctangent 1, which would be 1 minus a third plus a fifth minus a seventh. It's conditionally convergent. You see, it's an alternating series, but it's very slow convergence. That's not any efficient way to compute pi. Not today, but before the term's over, we'll talk about how you really do use series to compute pi. But this is theoretically how, but in practice it's not how. You won't live that long. Here's another example, a series for log of 1 plus x. So you could begin with the geometric series again, for which the common ratio is minus t. And it's convergent then when your common ratio is less than 1. And the sum, again, would be 1 over the first term minus the common ratio. So, in other words, this is the series for 1 over 1 plus t. And again, if you wanted to, you could do like I did at the end of the board and do the long division, divide 1 plus t into 1, and you'd get the alternating series. So then if you integrate term by term, you see this integral will be log, and then here, if you integrate as a definite integral, 0 to x, you'd have the integral of 1 minus t plus t squared. So your log 1 plus x would be x from there minus x squared over 2 plus x cubed over 3, like that. And you'd have plus constant, and if x is 0, your log of 1 would be 0, and all these powers would be 0, so your constant would be 0. And then this is conditionally convergent at 1, because you go 1 minus a half plus a third, and so on. Now, consider what is log of 1 plus x if it's this series, and if it is convergent at 1, you could put 1 there, and so on. So your log 1 plus x, when x is 1, would be log 2, 1 plus 1, and it would be this series. And again, this is very slow convergence. We looked at this series once before. You have, some of you anyway, received this handout, but you probably wouldn't find it right off, so I have it again here. What I want to show you with this handout is that trying to compute log 2 this way is very slow convergence. When we were first talking about alternating series, we had this example, and I said it was log 2 without showing you how I knew that. But you see, the way you know it is you get this geometric series, and then you integrate term by term as a power series, and that gets you the log 1 plus x series. And then you can put x equal 1 in. The only trouble is, it's like the pi over 4 series. You can't really get numbers out of it in any efficient way. You have one, yeah, that's the one I mean. If you look on the sheet for the alternating series, is for log 2. You see, if you take the partial sums, the red ones where you end up with a plus, you get these various decimals in sequence, which are always too big. And if you end with a minus, you get the blue ones, or I guess that's not blue, it's violet, and they're always too small. And the red ones are approaching log 2, although you would hardly know it from looking at the decimals, by decreasing to it, and the violet ones by increasing. But you see, we've done 10 terms there altogether, and we're not really at all close. The violet ones all say it's 0.6 something, and that's at least true. The red ones are still telling you it's 0.7 something. So that's what I mean by extremely slow convergence, slow enough that it's true, but it's basically worthless. So what would you do? Okay, so begin with a geometric series with common ratio t. And again, it'll converge for the absolute value of t less than 1, and the sum will be 1 over 1 minus t. And then you come over to here, and you integrate, and so you finally get minus log, you see the minus sign here, when you do your u substitution, gives you the minus. Minus log 1 minus x is the power series that you have here. So now we have the two power series for the logarithm. We have this one for log 1 plus x, that's alternating, and we have this one for minus log 1 minus x, that's not alternating. The coefficients are all plus. So suppose you add this to this, which you can do inside your interval of convergence, because you can do anything that you could do with polynomials. And so log, if you add these, you have log 1 plus x minus log 1 minus x, like that, and then the difference of the logs is the log of the quotient. And if you add here, half the time these cancel, because you have a plus and a minus, and the other half you're multiplying by 2. You have 2 x's gone, 2 times x cubed over 3 gone, and so on like that. So factor the 2. So now you have an alternating, well, you have a series of odd powers. It's not alternating, but it's odd powers corresponding to log of 1 plus x over 1 minus x. Okay, so say you wanted to get log 2. What x do you use? Well, set your argument here equal to 2. What fraction is x? Solve. So multiply here, and you have the numerator equals this 2 times the denominator, and collect terms, and 3x is 1 and x is a third. And you can see it works. 1 plus a third over 1 minus a third is 4/3 over 2/3, which is 2. So now log 2, using this, would be this common factor, and then you have a third cubed over 3, a third fifth over 5. Well, how good is that? Well, I just happen to have, I'm sure you're surprised, I've written out, and I have my log 1 plus x, and I have my log 1 minus x, and if I take the difference, I get the same series with the odd powers that's here. Okay, so suppose you wanted log 2, and you see I show you the calculation why I'd use x equal 1/3. So then, if you were setting this up, 1/3, write the decimals, then the x cubed over 3, a third cubed is 1 over 27, divide by 3 gets you the 1 over 81. Then a third to the 5th power over 5 gets you 1 over 1215. Write the decimal. So you could take your calculator and get the decimals. X 7th over 7, x 9 over 9, x 11 over 11. Well, notice if you did a third to the 11th power over 11 and got the decimal, you have 6 zeros before you have something. So if you were rounding that back, that would be 5 zeros and then a 1. And if you round it again, that would not influence the 5th decimal. So if you were trying to produce a 5-place log table, say, so you could guarantee your decimal for 5 places, which is what you have to do if you're really trying to compute something. You have to say, well, it's right for 5 places or whatever. That's all you get out of your calculator is a decimal that's right for however many digits the calculator will display. Okay, so if you add all this up, you see then that's going to give you the decimal point 3465773, and then you take 2 times that and you get the 69314, which is about what your calculator will say. Your 5-place table entry then would be 69315, and my calculator gives log 2, as you see, 693,14718. So this will get you a log 2 value in a reasonable amount of time compared, say, with trying to do it this way. So this is the kind of thing that people originally had to do to produce log tables in the 1700s, and then they printed up first 4-place tables and then 5-place tables and so on like that. It was a great deal of hard work, you see. You could do this for various numbers and then use your laws of logarithms. For example, if you got log 2 and you got log 3, then you can add, and that's going to get you log of the product is the sum of the logs. So log 2 plus log 3 will get you log 6, and so on like that. So you don't have to do the decimal work for every single number, but you have to do enough of them that you wouldn't really want to do that. But this is what people did, and corresponding things with the trig tables and so on. And if nothing else, it's worth going through this to appreciate other people's work. So then the others, remember that I gave you the test 4 last week. So if you were not here last week to get it, you want to be sure and get a test 4 from me. And the other thing I want to give you before you go is the take-home part of the final we've got, which is all sequences and series. We've got far enough into this chapter that you can start working on it. So this, as you see, has a cover sheet and is, there are 20 questions that are multiple choice, and there's 10 that are true false. So I expect you to mark the letter for the multiple choice and the T or the F for the true false, but don't tear this book apart. I want the whole book back, and then you can write on the inside all what you want to. It's printed just on one side of the paper, and so you can write on the back of the facing page or whatever you want to do. Okay, so this would be due whatever, what is it, the last week in the month. So that's, what, 2 weeks from now, isn't it? This is the 14th, yeah, the 28th or 29th. So. In one.